50 engineers. That's it. 50 people delivering 100 billion messages every single day to 2 billion users. For context, Twitter had 3,000 engineers serving a fraction of that traffic. How do you build something that lean and that massive? The answer starts with a post office and the smartest delivery system ever engineered. Let's feel the scale before we solve it. 100 billion messages per day is 1.15 million messages every single second. Not peak. Average. Your phone sends one message and somewhere, a server has 10 milliseconds to figure out if that person is online, where to route it, and what to do if they're not. Every single time. Most developers' first instinct, HTTP polling. Your app pings the server every few seconds asking any new messages. At 2 billion users, that's billions of wasted requests per minute, most returning nothing. Your servers melt, your bill explodes, and you still have delivery lag. This is the naive approach. It doesn't survive past 10,000 users. Here's the mental model that unlocks everything. WhatsApp works like a post office. You're the sender. Your contact is the recipient. The WhatsApp server is the postmaster. If your contact is home when the letter arrives, instant delivery. If they're out, the postmaster holds it in a P.O. box until they return. That P.O. box is the secret. WhatsApp didn't write their server in Python, Java, or Go. They chose Erlang, a language built by Ericsson in the 1980s to run telephone exchanges. Why? Because telephone switches can never crash. Erlang was engineered for exactly this. Millions of simultaneous connections, isolated fault handling, and zero downtime hot reloads. They were solving telecom scale before the internet existed. Here's what nobody tells you. A single WhatsApp server in 2011 held 1 million simultaneous TCP connections, one machine. Modern Node.js servers sweat at 10,000. The reason? Erlang processes weigh just 2 kilobytes each. Your OS thread, 8 megabytes. That's a 4,000x difference. WhatsApp runs 2 million lightweight processes per server like they're nothing. That's the whole trick. Each WhatsApp client keeps one persistent TCP connection open to the nearest server, always. Think of it as a telephone line left off the hook. The server can push a message to you the instant it arrives. No asking, no waiting. When the app goes to background on iOS, that connection stays alive, heart beating every 30 seconds, so the server knows you're still there. WhatsApp started with XMPP, an open messaging protocol that's been around since 1999. The problem? XMPP uses XML, and XML is verbose. Every message carries kilobytes of angle brackets and tags. At 100 billion messages a day, that overhead is catastrophic. So WhatsApp built FunXMPP, a binary encoding that cuts message size by 2 to 3 times. Same protocol, radically smaller packets. Back to our post office. When your contact is offline, their phone died, they're on a plane. Postmaster doesn't give up. The message goes into their P.O. box. On WhatsApp servers, that's a RAM-first queue that spills to disk. The message waits. When they reconnect, the server flushes every queued message in order. Then, and only then, the server deletes it forever. You've seen the ticks your whole life. 1 gray tick, the postmaster received your letter. 2 gray ticks, your contact's device received it. 2 blue ticks, they read it. Each tick is a separate act flowing back through the system. This isn't cosmetic. It's the delivery guarantee mechanism, the proof that store and forward actually worked. 1 tick means the message is still in the P.O. box. Here's the part that makes WhatsApp genuinely different. Every message is encrypted on your device before it leaves your phone. The WhatsApp server is just a courier carrying a sealed envelope it cannot open. This is the signal protocol. The same encryption signal uses. Even if WhatsApp servers are breached, attackers get gibberish. The postmaster delivers letters they can never read. 2 cryptographic pieces power this. First, X3DH, extended triple Diffie-Hellman. Think of it as both phones agreeing on a secret handshake before they've ever spoken. Second, the double ratchet. Every single message uses a new encryption key derived from the last one. Even if an attacker steals 1 key, past and future messages stay protected. That property is called forward secrecy. Let's zoom out and see the full system. Clients connect to edge servers via Anycast routing. Your phone finds the geographically nearest server automatically. Those edge servers talk to internal routing layers that maintain a global map of which server holds which user's connection. Think of it as a giant directory, like a phone book that tells the postmaster which post office to send your letter to. Here's the routing problem nobody talks about. WhatsApp runs thousands of servers. When you send a message, your server might not be the same server your contact is connected to. The routing layer maintains a distributed registry. Think of it as a global lookup table, mapping each user ID to their current server. Message arrives, lookup fires, message hops internally to the right server in milliseconds. Here's a simplified version of the routing logic in Python. The key insight: it's just a dictionary lookup. Is this user in the active connections map? Deliver immediately. Not there? Drop it in the offline queue. When they reconnect, flush the queue in order. This pattern, called store and forward, is deceptively simple at small scale and enormously complex to make reliable at billions of users. When a user reconnects, the server must flush their PO box in the right order. Critically, the server waits for an ACK from the device for each message before deleting. No ACK? Keep the message. This guarantees at least once delivery, the same promise your post office makes. Messages might arrive twice if the connection drops mid-flush, so the client deduplicates by message ID. Every time you see online or typing, that's a separate system called presence. Each device sends a heartbeat to the server every 30 seconds. Present state lives in a distributed in-memory store. Think Redis but sharded across the entire cluster by user ID. When you open a chat, your client subscribes to your contact's presence. Updates push through the same persistent connection. Fast, real-time, cheap. Presence is actually the hardest scaling problem. At 2 billion users, you can't store everyone's online state in one place. The solution: shard by user ID. User ID 000001 lives on shard 1. User ID 9999999 lives on shard N. Each shard is an independent in-memory store. To look up a user's presence, you hash their ID to find the right shard, then query directly. One hop, done. WhatsApp web, desktop, and your phone all receive messages simultaneously. Here's how. Each device has its own unique key pair, its own address at the post office. When you send a message, the server fans out N copies, one per registered device. Your phone and laptop each get their own encrypted copy. That's why WhatsApp web links with a QR code. It's exchanging cryptographic keys, not just logging in. Group chats seem simple. They're a nightmare at scale. For a 1,000-person group, the server fans out 1,000 copies of every message. Your phone sends once. The server multiplies. Media is even smarter. Photos upload to a CDN first. Then the message only carries a URL plus a decryption key. The actual bytes travel once. The envelope with the CDN address travels to every group member. WhatsApp didn't build Ejabberd. The Erlang XMPP server they started with is open source. They forked it, stripped it, and rewrote the hot paths. By 2014, with 450 million users, they ran roughly 200 servers. One server handled 2 million connections with P99 message delivery under 100 milliseconds for online recipients. That's the power of choosing the right foundation and not fighting it. Every messaging app makes different bets. WhatsApp, messages stored temporarily on servers, deleted after delivery, end-to-end encrypted always. Telegram, messages stored in their cloud forever, great for multi-device, but Telegram can technically read them. Signal, same encryption as WhatsApp, fully open source, even hides sender identity from Signal's own servers. Different trade-offs, same problem, wildly different solutions. This breaks everything you think you know. WhatsApp does not store your messages long-term. Your chat history on a new phone? That comes from your local backup, iCloud or Google Drive, not WhatsApp's servers. Their servers are a relay, not a database. The moment your device acts a message, the server deletes it. Their storage is a temporary post office, not a permanent archive. In a Meta or Apple system design interview, design WhatsApp is a top 10 question. Interviewers aren't looking for perfection. They're looking for 4 things: persistent connections over polling, store and forward for offline delivery, sharding the present system by user ID, and end-to-end encryption at a conceptual level. Mention the 2-tick delivery receipt. That one detail signals you've thought about reliability. In your next system design interview, say exactly this. I'd use persistent WebSocket connections to avoid polling overhead, a store and forward queue for offline recipients, and shard the present service by user ID for horizontal scale. Messages get end-to-end encrypted on device. The server is just a relay. Delivery confirmation uses a 2-tick ACK system. 1 tick on server receipt, 2 on device receipt. Let's trace one message end-to-end. Your app encrypts it locally, sends via persistent TCP to your nearest WhatsApp Edge server. Server looks up your contact's connection in the routing registry, routes internally to their server. If they're online, delivered instantly, double-tick fires. If offline, queued in RAM, push notifications sent to wake their app, flushed on Reconnect, then deleted. Under 100 milliseconds when online. The 50 engineers stat feels like magic. It's not. It's the result of 3 ruthless choices. 1. Erlang, which handles millions of connections without threads. 2. A protocol designed around the constraints, persistent connections instead of rest. 3. No long-term storage, which eliminates entire classes of database complexity. Simplicity at the architecture level multiplies your engineering team's leverage by orders of magnitude. In February 2015, WhatsApp launched voice calls. On day 1, they handled 100 million calls. Not after scaling up, on launch day. That's because the infrastructure was already there. Persistent connections, global routing, Erlang's massive concurrency. Voice calls are just another message type with stricter latency requirements. The post office was already built. They just added a phone booth inside. Remember the post office analogy from the start? You're now holding the blueprint. The persistent TCP connection is the open telephone line to your postmaster. Store and forward is the PO box that holds mail when you're away. The 2-tick system is your delivery confirmation slip. End-to-end encryption means the postmaster handles sealed envelopes they can never open. That's WhatsApp, 100 billion times a day. 50 engineers, 100 billion messages. The secret? WhatsApp is a post office that holds your mail when you're away and burns the letter the moment you pick it up. Next time someone asks you to design a chat system, start with the PO box. If this clicked, subscribe. We break down one system like this every day.